All right, time to do it up. Wow. Quite a bit of what a configuration nightmare that was. Uh, let's see if I am indeed live on the page. I'm gonna pop me a cough drop here. All right. So as I was saying, this is going to go on the YouTube archive for viewing later. People will be able to view this later. That being said, for the record, we are starting about an hour and a half late. Most of that was set up. Part of that was me. Keep in mind, I am sick right now, so I'm just kind of sucking it up and doing what I can. So if you hear me, I'm going to be eating some cough drops. And what we're going to do, we're going to get underway immediately, since we're so behind. Learning experience. We're going to pop open Visual Studio. And I'm just going to go down the line and address each and every topic. And we will go from there. Alright, let's do something like this. New project. I'm going to go new project. Let's see. We're going to want C++. I'm going to find myself an empty project. Empty project. Completely empty. And I will do this. Let's see, we'll do live stream 1. And we will put this in our code folder. Yeah, just in our code folder. 2013. No, just in the code folder. Getting kind of crowded in there anyway. Okay. Source files. Add. New item. Note it gives us a choice between a header and a source file. I'm going to pick the source file. And what I'll do is I will just call this main.c. Boom. Okay. So, basic program. We have got ourselves a compiling running console. So I can now kind of play with this to run some test cases and give you guys some insight as to what is happening. While he's downloading, I will do an example. So now a forward declaration. Let's explore this a little bit. Obviously we have main. Let's explore another function. Let's explore maybe void count up. Maybe for int I equals 0, while I is less than . I plus plus int Okay, here's a perfect example. I'm pretty sure this is relevant. So the first topic we're covering is forward declarations, and if you look right over here, you'll notice we have this error, count up, redefinition. They have different basic types, so it's confused. And we're not sure why it's confused, because it's pretty simple. We just want a subroutine that just does something that just counts counter up from 10 from wherever it may be. Now, if I were to do this, and now I'm going to go to build, and now the build succeeded. Whoa, holy moly, the build succeeded. What is the difference? Why is this right here? Why on earth is that thing so significant? And there's a couple of reasons that's significant. Most of them were covered in lecture. That we know we need to evaluate what are called the types. The C compiler, based on how your compiler works, the C compiler needs to know before it actually processes these instructions, and these instructions, which is called the body of the method, the C compiler needs to know what types it's expecting to be working with. And this is the return type. This is the type, and there might be multiple of them, the type of the arguments. Now, what's confusing for the compiler is the compiler cannot tell the difference between a set of instructions that take an int versus a set of instructions that take a null, and actually dynamically create methods that your assembly code can call before converting to binary. It doesn't know how to do that because there's a logical fallacy that's going on here in the recursive chain. Notice how main, back when I had just main as my program, the console came up, it ran just fine. I did not need to forward declare main. Well, that's because main can't be invoked in your code. It is the root node of your tree, if that makes sense. Now, to elaborate what I mean by the root node of your tree is if you have a tree structure. So let's look at a tree structure. I'm just going to, let's go to insert. Let's draw. Actually, I think I have shapes. Here we go. If I have a tree structure, there's that. And let's do another one down below it. Let's do another one down below it. And then maybe another one down below that, and below. This is going to be very rough, but we're going to illustrate a point. So if you notice what's happening here, so this is a rough idea of a tree. And so you'll notice this guy's the root, this guy is the parent of all entities, right? And then this guy has two children that he is linked to. And then these lovelies are linked to, this one's linked to one child, and this one's linked to two, respectively. Now the root is implied because the root's the starting point, so we know that every single program, just like every tree in existence, every single tree must have a root to be a properly formatted tree. And while there are exceptions to this, that is usually an exception that is done at the user space. The user space, which pretty much means the user doesn't need the root, the user just needs to work with the children. But programmers should always be aware of the root of a tree. It's just, you need to have a root so that you can, so if you need to move the whole tree, well, if I move the root, all of the children should move with it. For instance, if I move the root, all the children should move with it. But if I move this guy, well, alright, he's not selecting. Only him and his child go with it, right? So that's the idea of a tree. So now, here, main is the implied root. Well, we know every single program in existence must have an entry point. And this entry point is governed by very specific rules. These are much more specific rules than declaring a method or a function. They're very specific, and so we can reasonably assume that we should be looking for an entry point that governs and follows these rules, and this is one of those cases. So we did not need to forward declare this. However, any further functions that we want to execute within this root node, we need to tell the compiler what it can expect, because the compiler, there's less, the rules governing what we can make are a little bit less strict. We can do something like this. We can say, all right, well, maybe I want int Maybe I'll tweak it. Count up given and return. We don't need to declare a value anymore. We'll just say G. There we go. And then notice we have to return an int, so then we'll just do return G. Perfect. All right, so now notice I'm going to now build. I'm going to go here. I'm going to go to build solution. And notice here's something really interesting. Notice that the build succeeded. And I did not forward declare that. That's interesting. The build succeeded, and I didn't need to forward declare that guy. Why is that? Interesting. Interesting. That's worth it. That's worth a look. Return void. Let's try that. Yep. And all right, so I just figured it out. So the type that our compiler assumes that we are going to be returning an int. It assumes we're going to be returning an int. This is the root node, so there's an exception to this because we know that it's looking for a function named main to execute first, and so that's governed by a more stricter set of rules that we are following, so it works fine. But I figured it out. It assumes that, okay, you have not declared your function, so look, so I'm going to look, I found a declaration of count up, given, and return. It must return an int because it always assumes it's going to return an int. And oh, wait a minute, hang on, this returns a void. Wait, what? What's going on? And actually, where is that? Let me make sure I have this right here. This is where it is. The compiler scans main first, and it sees this method call, and so that's where it assumes it's going to return an integer, and down the road, then it's like, oh well, here's the definition and the implementation, but you're returning void, so it doesn't work. However, we can correct that. We can tell the compiler, because remember, a compiler scans a source file like this. It goes, that's how it scans the source file. So we can tell the compiler, well, hey, don't cool your jets, don't worry. We have, down the road, when you see this, it is void. When you see this, treat it as void, and it takes an int. And so it's all right, so if I build succeeded, works just fine. It works just fine. Okay. All right, so let me go back to. Okay, so I've got a question, a user question from Nick Martinez. Would you have to forward declare count up if it preceded the main method? That's a great question. So let's do that. So let's test that. So now if we have count up, let's comment out our forward declaration. Let's go to count up. Let's take this guy and let's plop him right before main. Let's do that. And let's build. Aha, build succeeded. Does that answer your question, good sir? So as you can see, you are incorrect because what happens? What happens? The compiler scans downward. The compiler scans downward, and it will hit void count up, and it will take, in one go, it will take both this as a declaration and an implementation, and now it knows because it encountered this first. It didn't encounter the invocation first. It encountered the declaration and implementation first. So the answer to your question is no. If you precede your methods with the before the main method, you do not have to forward declare. I'd like to take a moment and change topics, but first, before I do, are there any more questions about forward declaration? We move on to pointers, and we're going to start with a blank slate. So moving on with a blank slate and working on pointers. Alright, so we know we can declare integers. Say int, let's call this my integer. You can spell, Lambo. My integer. Let's give it a value of 10. And now let's do this. Let's do let's do this. That wants the format. Oh, dang it, I'm rusty on my formats. Dang it. Oh, let's see. Okay. Alright, here we go. So here we go. Good old pointers. So as you can see, I like this format for printing out a demonstration because now when I print the variables, you can clearly see at runtime what they are. Notice I had to comment out that last printf statement because can anyone watching the stream tell me why I had to comment out that last printf statement to keep my program from crashing? Any guesses? I've got my eyes on chat right now. And I'll give you a hint. It has something to do. Like, look closely with that green printf statement that I commented out. Look closely what I did to my int pointer. I just wanted to give you time to think about that. I haven't gotten any guesses, but I'm going to move on in the interest of time. What you'll notice is I am using a dereference operation. The asterisk is a dereference operation, and the asterisk tells us, it says, hey, get me the value at the associated memory address in my int pointer. Alright. Pretty much you can read it this way. You can read it as use the current value as a memory address, not a value. Because there's a couple ways you can do it. If we use something as a memory address, we're going to get back something different than if we use it as a value. Notice I initialized my int pointer, I initialized it to 5. When I printed out my int pointer, when I printed it out, I actually got 5, right? It's just a variable, nothing special. When I printed out my integer, I got 10. It's nothing special, it's just a variable. But the difference is with a pointer, now we have what we call layers. We have layers now. We have these same layers with a regular variable. Let me now add another printf statement and show you what I mean by these layers. Think of it as like a derivative and an integral. A derivative, you go down an operation, and integral brings you back up a level. So derivative goes down a level, integral goes up a level. I want you to picture the asterisk is like an and when I say up a level, what does that mean? It means it's a dereference. And I'll explain this in a little bit. I'll explain this more. And then the ampersand is like the derivative, because we go down a level. Reference. A reference, so when someone says, I would like to get a reference to this variable, they are talking about its address, because you are guaranteed to change the variable that you want to change if you reference it using the address. Now a value, if you throw a value around, well, a value is just going to change. A value may not necessarily be stored back in memory. I would feel much more comfortable explaining this via demonstration. My integer, my pointer, printf, perfect example. All right. So what you're going to notice is now I've added another line that it is essentially what I am comparing to the derivative operator is our ampersand. That is our reference operator. We can reference and we can dereference. A reference returns a memory address. Remember, a reference always returns a memory address. A reference always returns a memory address. A dereference always returns a value. And this value could also be a memory address. Does that make sense? So, I'll say it again. The ampersand is like the derivative because we are going lower level. We are now getting a memory address in the hardware. So when you ampersand a variable, you always get the memory address of that variable. When you dereference, you are following a memory address. So you're not referencing, you're not looking on the shelf and just like, what address is that at? That's not what you're doing. When you use the asterisk, the star operator, what you're doing is you are saying, well, I've got an address, I want to know what value is stored at that address. And that's what you're doing. So, as you can see, 129.09380, that is the address of my integer. We did not specify that, the operating system did it for us. The operating system did it for us. We know so the value of my integer is 10. The address of my integer is this right here, that long mess. So now let's do something different. So now we know my integer is not a pointer. It is not a pointer. But I'm gonna try something stupid. I'm gonna do a pointer operation to it. Oh, look at that. Error. Operand of star must be a pointer. So I want to take a moment now to show you guys the difference between this theory we're exploring and how the compiler is baby-stepping us and babysitting us and taking care of us. The truth is, at a very abstract level, the truth is any value can be interpreted as a memory address. The compiler, however, to keep us safe from making really dumb decisions, the compiler will not let us treat any type as a memory address unless we actually say it is. And the reason why we do this is to prevent epic confusion. Keep in mind, a number is a number. I want you guys to remember this. A number is a number. Like, numbers are all equal. This concept of data is all the same. Let me open up Notepad. The concept of data is all the same. Okay, that's data. That is data. That's a number. It's a really big number. That's a number. It's data. Guess what it also is? It also is a string. It also is a double. It's a character. It actually has more. It has several characters. It's a string. It has it can be a float. It can be a int. It can be a memory address. A number is a number, right? You choose how you interpret data, right? We know that there is a lot of different number systems. There are a lot of different number systems. This is binary. We can easily represent this in, in decimal, right? I don't know. I'm just pulling this out. I really don't know what that binary is, but now we're in decimal, right? Let's assume that this is actually, it's probably a lot, all right, let's be fair, it's probably a lot bigger than that, right? But let's assume this is like decimal. It's not that big. And, alright, so when you view this idea of data is just a stream of bits, right? Now we can view those bits as a decimal number. And we do that for convenience, because as human beings, it's very easy to view these numbers as decimal because we've been doing it our whole lives. But sometimes the numbers are a little bit too overwhelming, and sometimes we need to use hexadecimal to view them. And that's when you see those weird numbers that have A through F in them. That's hexadecimal. And that helps us quite a bit, because that really shortens the length of really big numbers. For instance, this is not an accurate translation, but maybe we did like 87 AF, and let's look roughly. This has 4, 8, 12, and then I'll just do, there we go. And then maybe cut that about in a piece. 1, 2, 3, 4, 1, 2, 3, 4. It's rough. It's rough. They're definitely not equal. I'm just kind of just doing this as an example, but you get the idea. So now this is a hexadecimal number that can express this decimal number, that can express this binary number, right? The underlying data is the same, and because of that, this value is actually equal to this value, which is actually equal to this value. A value is a measurement of magnitude. It's a measurement of magnitude. If I told you to take if I told you to take 87 AF steps north, that's the same number of steps if I told you to take if I actually said take this many steps north, or if I said take that many steps north. It's still the same number of steps. They're just being interpreted differently. One of the everyone's favorite way to express a memory address, because the numbers get long, is typically hexadecimal. So that being said, a number is a number is a number. The only reason we introduce a type to be a pointer is just so we don't get confused. So that we explicitly in our program, we say, hey guys, listen, I wrote this program. I know you're going to want to modify, you're going to want to mess with it. These things are pointers. These I'm actually working with memory directly. These are variables. I don't need to work with memory directly. Value storage is enough for me. But here I need to work with the actual memory. I actually need to do some referencing, and I need to use pointers. Now technically, we could technically remove because notice how pointers, when it comes to pointers, we have using the pointer symbols as an operation. We're performing an operation on my integer, and then this is the operator. That is an operator. Like plus, minus, divide, that is an operator. And what that operator does is, this is like a function call. Does that make sense? So if I had a function and I said int result equals my function, and I gave it my integer, right? My function. Now besides the point, I have not declared my function, but it returns something, and it returns a number, and if I gave it my integer, it returns something back. This is just a shorthand. This is not an actual function call, but it is conceptually the same thing, because this is an operator. This is an operator in our language that's actually doing something to this. And then this whole thing represents the result. So just like I can do int Bob equals my function result. So now I'm performing. So now I'm doing it again, right? Now I'm doing it again on the result. I could just substitute that for this. My function, my integer. Same thing. This returns a value. So wherever the return value is expected, I can plug that into a function parameter, and it will get passed, and it will do what it wants to do. So that's a valid call. That's valid. Which is why something like this is also valid. Now it's not. Now the compiler is going to try and protect us. It's not going to let us do it. But watch this. We can do. Now see that? See that? Doesn't like it. Doesn't like it. This is like a function. It returns the address of my integer. So then we get a address back. But here's the interesting part. You can't, it's impossible. You can't get the address of an address. You can't do that. Conceptually, we could do it, but you'd get nonsense. And there does not exist a single useful, practical need for that. So the compiler says, all right, well, we're in good compiler design. The compiler says, all right, well, I'm not going to let them just blatantly make really bad mistakes that will crash their program. So I'm going to complain. I'm going to complain and say, no. You can't, an address does not have an address. An address is an address. Does that make sense? So you can't do that. You can't double reference. It doesn't make any sense. And the reason is this, because what does my integer represent? Well, when the compiler scanned it, it created a table. It needs to keep track of the variables as long as the program's alive. Part of the scoping principle and practice. And now this table, when it has the name of the variable, it's got the current value of it, and it's got the address of it, among other things. And it needs to know where it is in memory. So when you do this, well, that makes sense. You need to do that. So yeah, so I can remove this, and see, and that makes sense. Yeah, that makes sense. I can reference and get the address of this variable because it is an actual variable. It is an actual variable. But you can't do that. It's like the conceptually you could. The idea is the same as saying, oh, I'm going to take my function, I'm going to pass into my function another result of my function, and we're just going to keep doing that. And then I could do it again. I could do my function. I'm going to pass in. I could just keep doing that, right? See? And the compiler doesn't complain. The compiler isn't complaining. Compiler's like, oh, yeah, that's legal. So that's like doing this. Right? That's like doing that. So I want to take the result of this reference, and I want to reference that. And I want to take the result of that reference, I want to reference that. But the reason why is because you can't, once again, a memory address does not have an address. It is an address. So that's why it won't let you do that. And that's why it only lets you do it once. Now, on the other hand, int a. So let's say, let's try this. So now let's go the other way. Now let's dereference. Well, the dereference function, what does it take as input? It takes a memory address as input. Okay? Just like what I was explaining before, we can do dereference, we can keep dereferencing. And that's where double and a pointer to a pointer and a pointer to a pointer to a pointer start to come into play, which we'll get to. I will show an example here. But it's interesting because no matter how many star operations we do, it still complains. Well, as I said before, it's not a pointer. It's not a pointer. Hypothetically, we could do this. And hypothetically, we could do it because a number is a number. Like I showed you in TextPad, unlike with the reference operation, the ampersand, with that reference operation and the ampersand, notice how you can only do it once and then you're done, and it's literally impossible to keep doing it. It literally is, because because an address doesn't have an address. An address is an address. But here's the crazy thing. We can do multiple star operations because numbers are numbers. Data is data. And so if we want to read data as a memory address and get the value there, if we want to read, we can do that because a number is a number. A memory address is a number, it's data. A value is a number, it's data. It is data. It's how you read the bits that counts, and that's where type systems come in. An int, a float, a char, a string, these all define rules for how you read the bits. So we can actually, technically, we can keep doing that. We can say, all right, here's a number. I want you to use that number as a memory address, and I want you to go to the value. I want you to get me the value of that memory address. And then I want you to use that value as a memory address as well. I want you to use that value as a memory address. So I want you to go get me the value there. And then I want you to use that value as a memory address, and then go get me the value there. So now what I'm going to do is I'm actually going to tell the compiler, hey, this is okay. We can get away with this, so I'm going to do this. Oh, interesting. the error changed. So I did a cast. I cast it. I said, hey, I want you to interpret this bit. I want you to interpret this as an int pointer. I want you to do that. And it's going to be like, are you sure? It needs to be a pointer, and I'm not falling for your cast. So it's really smart. The compiler knows, because the compiler, here's the thing, because I'm telling you the conceptual idea behind this, but the compiler imposes additional rules to hinder your full use of the concept unless you actually know what you are doing. Because the compiler says, hey, listen, the odds are, you need to strictly type your system here, but if you want to take off all those security measures that I'm doing, you can do that, but you got to do it explicitly. And there we go. It doesn't complain. I cast it. It does not complain. Here, right? Oh, complaining. It's complaining. Must be a pointer. I'm like, all right. Well, you want to know what? It is not a pointer, but I'm going to say, but treat it as a pointer. Oh, okay. I'll treat it as a pointer. It doesn't complain anymore. But now watch this. Now I did not declare my function, so I'm gonna comment that out. I'm gonna run this. Oh! Error, big error, unhandled exception at this lovely. Oh, look at that lovely hexadecimal number. That's hexadecimal. See the C and the A? That is a number. A number is a number. A number. That is a hexadecimal. Found it. Access violation reading location. This, when you get an error like this, what does that mean? That means you tried to dereference or read operating system memory. There was memory you had no business reading and you tried to read. And I'll tell you why that happened. And I'll tell you this, it is not because my integer, it's not because my integer is not a pointer. No, watch this, watch. I will make it a pointer. And I will remove our cast. And I will run this. Same thing happens. And the reason why that same thing happens is because the value, the address 10, that is too low. That is a low address. That is where we cannot read there. I will now make this a more appropriate address. And let's see if it throws an error again. No, yeah, see? There was something else. That's the thing. That's the thing with literally referencing memory. You don't know what's there. You don't know what's being stored there. You don't know. You just don't know. So, what am I going to do? So, here's what I'm going to do. We want to get... Notice how this is the address of my integer. I'm going to comment this out. Make that 10. Look, the address, this here, notice how that's always changing? That's all, you never know what that's going to be. It's always changing. Because the operating system's always dynamically working with it. You never know what that's going to be. There's no guarantees. But we know what the values are going to be. And now, I will show you, now you're like, okay, well, Lambo, well, how do I get the address I want to manipulate? All right, so you do it, you let the operating system allocate the address, and then you assign it to your pointer, like as follows. So what I'm going to do, so I'm going to say instead, actually, I want to print that, and let's do this. Let's say, so int my integer equals 10. Int my pointer equals the address of my integer. Aha! There we go. So now, my int pointer is pointing to my integer. Okay, we're getting somewhere now. Which means now if I uncomment this line, let's do this. Let's do my int pointer is the address So you're going to see the address twice, right? You're going to see the address twice. And then, furthermore, printf. Now let's get interesting now. Ampersand my int pointer equals. Aha. Yep, and that makes sense. All right, let's look at this. This is a very interesting result. At first, I thought the exercise had backfired on me, but no, it actually this is actually legitimate. So, take a look. My integer is 10. The address of my integer is this. We set my int pointer to be the address of my integer. So without doing the ampersand operator, my int pointer, the pointer, is the value, its value is the address of my integer. Which means when we dereference it, it says, okay, well, get me the value at this address. Well, that's obvious. That's the value of my integer. But now let's look at something different. What is the address of my int pointer? It's this. It is, see how it's changed it a little bit? They're close together, 174, 32, but that's 128, that's 116. Isn't that interesting? It's interesting because the int pointer is a variable too, and it needs storage. So it is being stored somewhere. So because it needs its own storage. Anything that needs storage, that's called being byte addressable. Memory needs to be byte addressable. You need to be able to, it needs to have a place to live. If it doesn't have a place to live, it's not going to be in the program. It won't be there. So this guy, where is my int pointer living? It's living here. If I print the value of my int pointer, I get this. What do I print? I get the home, I get the place where my integer's living. And then if I dereference that, I get 10. Or if I just use the my integer variable, I get 10 as well. All right. So that was the first bit on pointers. Any points of confusion? I know we've got about 6 people watching. I'm curious, are there any points of confusion? I'd like to get them resolved ASAP. Go ahead and ask your questions. If something doesn't quite make sense. And we've got another watcher. Just a heads up, we are now taking questions, if anyone's got any questions. All right, question from Nick Martinez. With respect to an array X, is a pointer equal to the address of X equivalent to a pointer equal to X? All right, very, very interesting. Okay, let's now bring in the idea of arrays. All right. So now let's experiment with an array. If I have an array, all right, let's see. All right, let's start with something basic. I just want to get what I do is, as an engineer who's constructing software, I always want to know what my default state is in my program. All right, cool. This is kind of interesting. It's kind of the reason I wanted to point this out to you guys. I have not initialized anything. I have not assigned any values. What I'm doing is I'm showing you what in C, and also, and this happens in C++ too. I want to tell you guys about a time I was working with Unreal Engine 4. It's a magnificent game engine. It's free and open source. You just give Epic a 5% royalty. They are my heroes. And it's completely open source C++. Unreal Engine 4 is amazing. And we were making an application in our research field, and we're messing with direct addressing, and we're looking at memory addresses. And our clock, we were importing a clock from some data over a network, and what was happening is we were creating a clock, but our timestamps were getting all messed up. We were getting negative time, and we couldn't figure out why we were getting negative time. Like, why was it calculating, like, from the time of the first-person shooter started to the end, why were we getting negative time? It's because we didn't initialize our values. We assumed they would be initialized for us. And so what was happening is, this was what was happening. If you look at memory, memory addresses are actually used for default initialization in C and C++. It's gibberish. It means nothing. So I just wanted you guys to be aware of that. And it's complete gibberish. And as you see, it was negative. Because it's negative, it's because we're reading it as a signed integer. In its true form, it is an unsigned integer, because it's a memory address. And that would give you the actual memory address, hardware-wise. But this is, we're reading the memory address bit stream as a signed integer, so we get less space for magnitude, but we get the ability to negate it. So there you go. Now, on that note, so now that you've seen that, so now we're going to initialize this. There we go. Cool. So we've got ourselves values that are just a very simple quadratic, set of values going up. Just I squared. Pretty simple. We'll use that as our example. Now what we'll do, we'll do printf. We're going to want to let the program know we need some space now to make additional calculations. So I'm going to make some space. And what I'm going to do, comment all that out. Take this. And throw this stuff over here. I will make this source file available afterwards. I will make the source file available. Alright. Now I gotta figure out how we're gonna approach this problem. All right. Well, let's just kind of keep it. Let's keep this in sync with Nick Martinez's question. Let's say let's do this. Let's do printf. So we're going to do a little bit of a comparison. Let's see. Okay, so let's do that. Let's run this. Let's compare. So it's very interesting. So, and I want to make sure I passed in the right thing. So my int array, at my int array, and ampersand my int array. All right, so notice it looks like they're the same thing. We get the exact same memory address back, which is interesting. You start to wonder, all right, why do we get the same memory address back? Well, because an array, the way the square brackets work is the square brackets are essentially a function, just like the star and the ampersand. They say we're going to work with indexing. And here, you want to make this a little bit more clear. Let's get this a little bit more clear. We can make this even more clear. Now don't freak out. Don't freak out. The address has changed, but that's just because we're running the program differently. Watch, see, the addresses are different. And watch, if I were to run the program again, yep, they changed again, see? Like I said before, the memories, you never know what memory is going to be. The operating system's doing it, so they've changed. But anyway, you do see a pattern, though. There's a pattern. Notice something very interesting. So my int array, because we are working with an array, and we're going to do operations on the array for indexing, essentially, since these operations specify which index we're going for, you need the array, plain and simple by itself, is essentially a pointer. It's essentially a pointer because it needs to point to an index. It needs to know what index it's going to point to, and by default, it points to the first one. And if you dereference an array without an index, well, once again, it just defaults to the first one. But notice, there's something going on here. My int array 0. Here's the first one, and look, here's the second one, the third one, the fourth one, and the fifth one. See, in 8 plus 4 is 12, plus 4 is 16, plus 4 is 20, plus 4 is 24, and an integer is 4 bytes. 32 bits, 4 bytes. It makes sense. So that's byte each, because remember, that's the crazy thing. The crazy thing, every byte has an address. That's the crazy thing, because bytes can be set. And so this guy right here, 3604.108, this is the byte that starts our first integer. This is the byte that starts our second integer. And there are a total of 4 bytes here, because 4 bytes later we get to 12, 4 bytes later we get to 16, and so on and so forth. So there you go. Notice they're in series. Why are they in series? Because we allocated an array. Notice printing, but here's the interesting part. So the ampersand makes really no difference for the array without an index. But once you throw an index on there, see the difference it makes? Now you're getting a value. Now you're getting a value. Here you're getting an address. Now, Nick, does that answer your question? Excellent. All right. And hello there, Pedro. Would you like to ask a question? I will now open the floor up to questions again. All right, there we go. I do that. I'm going to defer to the PowerPoint. Well, there's a possible chance. Let's see. Make some notes at the top of my source file. Slide 22. Okay. All right, so no questions. So I suppose, let's see. Let's conclude with thinking we can conclude. We're gonna want. I know there was there was a request. There was a request for heap versus stack. So memory allocation. And I believe let's see. Well, let's take a look. So let's say, so we're looking at this, what we're doing is we're looking at this array. Real quick, before we close for the day, before we finish up, I'm going to just briefly talk about if this array was actually on the heap, not on the stack. So the stack and the heap, I'm going to have to make a better diagram for that. I think I actually have an image somewhere. A really good one, too. Let's see if I have it. Let's see if I can pull it up. That's not great. This will have to work. That looks horrible. Alright, this will have to work. So, this gives you a pretty rough idea of the slice of RAM that every program gets. And you'll notice we've got the stack, and we've got the heap. They go towards the center. And that we have the heap starting pointer and a stack starting pointer. We have high address and low address. And every program gets a slice of this. So, not of this particularly. This is the slice that every program gets. So now using this, so what happens is when we go the stack is responsible for holding function calls. The stack is also responsible for holding and working with regularly declared variables. Now, the heap. How do we work with the heap? I'll show you. The heap is what we call is a dynamic tool for dynamic memory. So now, let's try this. Int my int array. Let's do this. Int pointer my int array on heap equals new. Oh, what did I mess up? I messed something up. Oh, it's probably. Oh, I know why. I know because I know exactly why. So I'm using C++ syntax. This is C. I'm using C++ syntax. Shame on me. Alright. Cool. All right. Okay, so 1, 2, 3, 4, 5. Cool. Awesome. So you'll notice something very interesting. So there's several different, and now keep in mind, the new keyword that I was using before is strictly for C++. We will come to that later. Currently, this C in and of itself, just plain old C, uses memory allocate, clear allocate, and reallocate malloc, calloc, and ralloc. Calloc, I just use calloc by default because notice how something interesting has happened. Oh wait, hang on. Let's be very clear. Let's be very clear about it. Notice how my interarray on the heap. Notice how it has been initialized to 0. That is because I have used calloc. Now here's something very interesting. So now I will now change it to malloc. And you will notice that no initialization has occurred. Just the raw values that were there last time, they're there. Whatever leftovers, whatever's there, not really useful. So now you can see why calloc is just so much more appealing. Keeps it pretty clean. Okay, so now you'll notice that's on the heap. So, and this is a method that is called, and this is only for C. Normally you'll use new and delete, but that's calloc. And now furthermore, let's make sure we are safe about this. Okay, now what I'm going to do now there should be an error. Oh, duh. Never mind, hang on. Wrong error. There we go. Was it an error? No, you know what it was? It just gave me leftovers is what happened. Okay. I see. So the memory got freed. But what ended up happening is, well then maybe let's try this. Maybe it just gave me the address. Let's try that. Let's see how good it is. Wow, all right. Well, on that note, then we might as well see what everything is. So pretty much when you work with the heap lets you specifically place memory where it will always be accessible. That's the key. The memory is always accessible, and the scope of declaration isn't as big an impact. Let me give you an example. I'm going to create a new subroutine. That may not be void depending on what I do. Let's see. Got that. So we got zeros, then we got gibberish. That's interesting. Zeros, gibberish, when we released it. Okay. So now what you've got to do is when in C, when you use calloc, malloc, or ralloc, what you end up doing is you go to the heap, not the stack. You go to the heap and you carve out some space on the heap for some data that will not leave the heap until you call free on that data. Notice how you can see when I run the program right here. When I call calloc, notice how calloc will allocates and clears, and then when I free it, I free the memory, so it no longer is cleared anymore, and it's subject to be reused. And in this case, we are getting gibberish now. Now we're getting gibberish. We're not getting actual useful data. So that's this idea of calloc. I'm just using calloc because it's by preference. You can use malloc if you want, but it's just by preference. Like if I were to switch that to an M. Yeah, see, it gives, you don't really know what you're going to get. It doesn't clear it. But then when it is freed up, it all becomes the same because it now can be subjected elsewhere. And there's a chance not only do the values become absolutely ridiculous, but there's a chance that you could get a null pointer exception or an access reading violation if you're not careful with that. So it's still giving you the bits. It says, yeah, I've got no problem giving you these bits, but you might get in trouble for using them. In this case, we are not. So once you call free on something, you have to be careful. You don't want to use it anymore unless you reallocate something more specific. So that's the comment on that. What we'll do now is I will demonstrate the heap and the stack and the scope. When we make memory, we're going to do the following. Trying to think how to best do this. All right, here's my thought. There we go. All right, that's what we're going to do. Alright, so under make memory, I am going to do some allocation. So we're going to say, alright, so we've got, let's do int my int equals. Let's actually do this. Let's do int pointer my int pointer equals calloc. We only want one. Then size of, and we want size of integer. Let's see. There we go. All right, we'll do that. Alright, so we've got two functions, and one of them allocates a memory on the heap and returns the pointer to that memory. The other actually is going to take that address and is going to read it. It's going to do a printf on it. We're going to set it to 5. Okay. Notice we're setting the value, not the address. The value is being set to 5. The address is returned by calloc, and then it's going to figure out what the heck it's going to do it itself. All right. Then we'll pass the address. All right, so there we go. So now what I'm going to do, so now I'm going to work, because, you know, data is data, so I'm going to work with ints. All right, let's see what happens. And sure enough, look at that. So it works. The value, we read a value of 5 right there. As you can see, if we go through the code, you'll notice that in the separate method, I indeed set the value to 5. But now, let's make this interesting. Now let's declare something on the stack. So I've just set on the stack, I've made an int and initialized it to 5. What I'm going to do now, I'm going to return the address of my int. Let's see if it behaves. Notice we did not get 5. We got gibberish. We got gibberish. Why did we get gibberish? Does anyone have any guesses as to why we got gibberish? The value in question is this guy right up top, right below read memory. And if we go through the code, so what happened? What are we doing in make? So in main, we make a label make memory, and we call make memory, and we take the address. Make memory returns an address. And we put the address in an integer called address. Here's make memory. What we're returning, it worked when we returned a pointer with calloc. When we used it on the heap, it worked fine. But now we're just declaring a regular integer, not a pointer, and we're putting it on the stack, and we're returning the address of my int. And then you'll notice that address goes in here, and then we read the address. Well, read, what do? We just take the address, we make a pointer, we set it equal to the address, and then we dereference it. But when we dereference it, we get bogus. Now I could understand if we did not dereference it. If we just printed my int pointer without the asterisk, well then obviously we would get some sort of memory address. It would be gibberish. But with that asterisk, we should get 5, and we don't. And now I will reveal why. It's because we declared this on the stack. And so what happened was make memory, the method make memory right here, make memory finished. Make memory finished executing because when it started execution, make memory got pushed onto the stack along with all the local variables that it needed to run. But when make memory finished, that got popped off the stack along with all the local variables it needed. When we worked with the heap, well, the heap doesn't change unless we make it change. The stack is always changing. The stack is in a constant state of change. So if you want things to work across methods and across time and across stack changes, you want to work with the heap, not the stack. The stack is really good for local variables that you don't need when the method terminates. Now, here's the interesting part. If we had indeed embedded make memory in read memory somehow, if we had taken make memory and embedded it in read memory, or alternatively moved the contents of read memory into the make memory, well then this would work. Watch. Interesting. So make memory. Make memory. Values 5. Read memory. Bogus. Absolutely bogus. No good. That's your answer. That's why. That's why we're having trouble. So, that is the difference between the heap and the stack. If you need to manually work with your own scope, you use the heap. But if the scope of a method is suitable for you, then you use the stack. In the review folder, I posted a document of a stack data structure versus a queue data structure so that you are familiar with how those work. The stack functions precisely like a stack. It pushes, it pops, and you can peek and see what's inside. By inside, what is on the top. You cannot see below it. And that is a typical stack. And that is how our stack in every application works. And the heap is random access. The heap you access not like a stack, but like a typical massive array. And so this now gives us insight as to why why this value, why this value becomes absolute nonsense between heap and stack. On the heap, on the read memory, if we used a heap value, it actually worked out just fine. Alright, I'm going to call it quits there. I'm going to call it quits there. I'm going to apologize for the late start. And I'm going to apologize for the late start. Let's see. Alright, I'm going to... Yeah, okay, I'm just making sure my audio is still working. And if you've got any questions, go ahead and send me an email if you've got any questions. But I'm going to call this quits for now. I'm going to post this so that others can see it as needed. Feel free to skip through or scroll through parts where I was just kind of setting things up or doing some research. If there are any further outstanding questions, shoot me an email, and we will get those cleared up as soon as possible. But I believe I'm looking through everything. I think we managed to address everything. And I will make sure that from now on, I'll make sure my announcements actually post, because I might have last announcement I post, I might have navigated away from the page too soon, and so consequently it did not post. So my apologies. And I will see you guys next time. For those who are curious, we are on this week for our review sessions. I am not working the full day Friday. So we are on for in-person review this Friday. And that will conclude our first live stream. I need to rest because I'm not feeling that great. Anyway, enjoy your evening, email me with questions, and have a good night.